So the Cerebrus, supports training with much larger inputs, and we have a few functionalities that usually requires code change that we natively support, such as gradient checkpointing, activation, eviction, and gradient accumulation. With this, you can train longer sequence lengths on a single system, even up. So in today's example, we'll talk about going from the 2K to the 4K, but in general, you can run, even with up to 50K MSL with no code change, or using any of the more recent techniques like flash attention and so forth to get to these larger MSLs. This is just with your traditional model with no code change, same model that we were running earlier. You can do it. On the right, you can see how the memory requirements grows as you increase sequence lengths for a GPT-J model, which is a slightly different architecture than the GPT-3 that we're running here, but still encapsulates similar behavior. And then as part of this, I'll show some of these new techniques that we've built natively into the system as well. And again, as you will see soon, all these changes require no special code. We'll still be using the exact same code base, same run.py, and I'll walk you through the YAML changes as well. Now, you've seen the slide earlier. There's one of the reasons why we, one example where we've seen larger sequence lengths having tremendous value. This was work we did with Argonne National Lab last year for the Gordon Bell, where we were studying the SARS-CoV-2 evolution dynamics with these foundational models called the GenSLM, where we were able to run like a 250 million parameter model, and they were able to reproduce the results on a GPU. And then when we went to the 2.5 and the 25 billion, they were no longer able to run these at these larger max sequence lengths out of the box, right? For these demos, we were running at 10,000 sequence lengths rather than the traditional 2,000. But the Cerebrus hardware can support up to 50,000, with getting to 100,000 in the roadmap coming out pretty soon. So I'm going to switch over, and we're going to start with the 4K MSL. So similar to the other ones, again, I'll quickly show you the YAML difference, and then we can go into the actual run command as well as what the results look like. So as you can see here, there are 3 changes. I've changed the data set. Previously, I was running on OWT for 2048. I'm running on Pile with 4096. Obviously, the max sequence length has changed, and correspondingly, I've also increased the max positional embeddings. And one of the features that we talked about, I've enabled grad accumulation here. I'll talk a little bit briefly on grad accumulation a little later, but these are the only changes really for me to go from 2048 to 4096. This remains true even if you want to go to, let's say, 30K or 50K. As you can see, I'm not changing the batch size or anything like that. You can still keep your batch size essentially the same because we have things like grad accumulation enabled. Now coming to the run command, again, we're still in the same directory running the run.py with weight streaming. As you can see, the difference in the larger context is above here, where we're only changing the data set and essentially the max sequence length. Again, we're training it, the same mounts, everything else remains the same from the previous experiments. There's no other change needed in the code or anything. This is just using our models to essentially as is. And yeah, let's get started. And while this gets started, I know in the previous few demos, I've been showing some of our tools with the CSCTL or TensorBoard. Are there any questions about that I can help clarify or answer that people have? So this run will take a little bit longer, mainly because we're running essentially a bigger model with a larger sequence length. as we saw here, the memory requirements and the compute we're going to be doing does grow as you get larger sequence lengths. So this will take a little longer than the ones we ran before, but shouldn't take long as well. And it's important to keep in mind that these demos we're running in fairly short time, in order of minutes, and we're essentially training 50 million, 100 million tokens here in each of these models, which really, you can see it's quite easy to get started and running on our systems, but also with the huge performance benefits, your results come back faster, which helps iterate more, try out more things, and ideally help come up with best solutions. Similar to the previous runs, we're compiling the model. If anyone's curious, I can show the CS-2 tools again to show how it's queued up and things, but I think we've gone over it now a couple of times. So unless there are questions on it, I'm just going to keep the tensor board active on the other side. As you can see, compile success completed, and now it's spinning up the execution job. So there's a fair bit of information on screen here. As you can see, it's checking to see that the system is available and it's waiting to be given access so it can start running. This usually happens in the case where someone else is queued up ahead of you and their job is hasn't completed yet, so the system is not available. So it will tend to wait until the coordinator is ready. In this case, we should be the only ones running, so we should be okay. As you can see now, it's time to execute on one system. And I'll bring back the tensor board.
Vishal, we've also got a question in the chat right now. It says, not related to the current topic, but for training BERT-based models, if a custom tokenizer has already been trained using Hugging Face, do we have to do anything special to use that within Cerebrus?
So we do support BERT-based models as well. If you're using a custom tokenizer, you can do it in your data preparation as well, so that it's already converted in the right formats and things, and then at that level you won't need to do anything specific. So later on I will walk through some examples, well, not too much in detail, but we do have some tokenizers where we already have, which are compatible, let's say like Hugging Face and things like that, so you can use it. Constantino asked a question about our scheduling. So there is a way for you to essentially set up via a batch and have like a time limit. The way that's done is we do have an integration with Slurm on top of our orchestrator. So this happens when you're deploying the job from the user node. Like, so essentially from your terminal here, you can launch it via Slurm, and through Slurm, you can specify a time limit for how long your essentially your S batch jobs can be, how many you can queue up as many jobs as you want, and you can specify a global time limit as well as a local time limit per job. And at that point, so then that would essentially kill it and free up and queue up the next set of jobs. And you can so that is, we do have that level of support at one level above. But if I do know ANL uses Slurm for other things, but you can actually install Slurm on the user node and use through our Slurm integration, that mechanism. Constantine, I don't know if that answered your question, but let me know. So our queuing mechanism wouldn't wait for all the CS2s to be available. So if two users are online and each queue up a single CS2 job, that would work fine. That won't have a problem. You can run two jobs in parallel there, essentially. Or if, let's say you have 16 nodes, right, and you have 8 people each running two system jobs, all 8 will run in parallel without a problem. But if you have somebody running a 16 node job, and then someone wants an 8 node job, then they would have to wait till 8 nodes become available for them, essentially. And in terms of the priority order there, that depends on how you can essentially control that through Slurm, essentially through the same mechanisms as you would for any other resources at the cluster level. So it wouldn't be within the queue, but it would be from the user node level based on access. So essentially the control would be with ANL's sysadmin or whoever is maintaining the user nodes, essentially, or maintaining the Slurm integration. And things like compile and things will happen as soon as there's a different set of resources required for it. And we do account for it, and we will launch those as soon as that becomes available. So even if you have no systems, available, you can still go through a compile and have your model essentially ready to go when you get the resources. The Slurm setup is built on top of the Kubernetes, so they coexist together, essentially. The Kubernetes is within the appliance. The Slurm would be at the user node level across all the users. So I think in ANL's case, on the ALCF case, there are 3 user nodes associated with these 2 jobs, with 2 systems. And so the Slurm would be across those 3 nodes. And that would essentially coordinate with the K8 setup underneath. Yeah, just to clarify, the K8 setup is within our appliance to queue up jobs to be deployed within the appliance. The Slurm integration happens at a user node level. So that would would also even control the resources on a user node. Say someone is doing some heavy pre-processing and you don't want that preventing you from running on the system and things. So you can still control the behavior on the user node itself, as well as introduce timings and things like that in the cluster as well. So Slurm coexists. It doesn't replace K8. Right. I do not think at this time ALCF has Slurm. I'm not fully aware of the details on what's required for it in terms of what security measures or what rules ANL has specifically to enable those things, but I'm sure Bill or Murli can explain this. There's a question on, can we see the execution trace? Do you mean in terms of when beyond what is already shared on the screen, where it's saying, okay, we're now sending waits, now we're training, saving checkpoints and so forth? Or because that gives a certain level of what the execution current state is in real time. And then obviously there are logs that you can look up as well to see what's happening as well. If you're wondering on whether you can see things at a level deeper where you're seeing when waits are actually being transferred or when they're coming back, what happens concurrently, some of that is available. I think, again, a lot of that is available at the sysadmin level, but there are some tools that are available for you to be able to access those logs as well. They tend to be more verbose just because there's so many things happening underneath. And so you would need some help in going through it. But if there's a specific use case that you're looking at to trying to understand what's happening and things, I think we've shared details on how to reach out to us. So I think we can take some time and go with you on that deeper. And yeah, so as we can see, the training has started. We're now running again on one system with minimal changes to the YAML file with no code change, essentially double the sequence length that we were running in the previous demos. And yeah, and that's pretty much all that's needed to run larger sequence lengths. You just specify your new data set and specify the large sequence length corresponding to it. And that's pretty much all that's really needed. The loss is higher here. Again, I haven't changed the YAMLs for the config to converge the best way and things like that here. This was just mainly to show how to get started. So again, we're only running for a few steps, but yeah. Sure. And while we wait for this run to run, I can talk a little bit more about our grad accumulation and how that works. As I mentioned, we used this recently, earlier last year, for some of the garden well work that we did with ANL. And one of the key techniques that is now integrated is the UCS grad accumulation, which is again in the YAML file. It's just you just set it to true. And the way to think about it is we essentially have a global batch. We break it down into sub batches. We, based on the memory constraints and things, we all automatically account for it and figure out what's the right mini batch that needs to be specified. They go through the forward pass, they compute the loss, they generate the gradients, we accumulate them on the memory X, and then they're fed to the optimizer. This works whether you're running on a single system or N systems. It scales just as well. And with this, you can essentially go to larger batch sizes to fit your needs, as well as, and as you get to larger models, you don't need to compromise on running smaller batch sizes because of the memory constraints. You can still essentially fit your largest models on a single system, or scale it up to as many systems you want through these techniques. This handles things like the accumulation of the losses and things like that as well. So all of that is handled underneath, and you as a user don't need to worry about how do I figure out what's the right optimal mini batch that I need to specify and things like that. All of that's handled by our compiler. So a longer question. Sorry, I'm just reading the comment.
Here, as you're reading it, Vishal, I'll say it out loud for anyone.
Yeah, I guess anyone who's not able to see the chat. So the ANL Gen SLM work also involved a diffusion model to handle larger context lengths than what the encoder-only architecture allowed. In such a case, what is the upper limit for the context length when the CS-2 is used for the application? I think currently I'm not too aware of the details of the diffusion model top of my mind. But in your encoder-only architecture, we do, without supporting any of the newer techniques like flash retention, we can go up to the order of 100,000 for context length. We are in the works of trying to increase that even further. You mentioned for human genomes, you can go up to hundreds of thousands that may be needed. In theory, yes, the CS2 should be able to handle that. Again, it's not yet ready today, but we are working towards it.
That said, I think a lot of the limitations of the CS2 haven't quite been found, frankly, because not all use cases demand everything that the CS2 can provide. So if that's a research area that you want to explore more, we definitely love to find you in our Slack channel with ANL, explore that a little bit more, and can motivate some of the work on our roadmap.
Yeah, absolutely. Tarak, if this is an area of interest for you of larger sequence lengths, if you're not already on our Slack channel, I think Moodle can help add you there, I think. Or you can send us an email and we can add you to it as well with the details and things, and we can obviously dive deeper into your project. As we get closer towards the end of this run, see what the tensor board looks like. So as you can see, we have 4 runs here. Let me make it a little bigger without the smoothing as well. You can see obviously the 1 system and 2 system runs essentially overlapped each other. Their sparse train started off a little higher, but ended up converging the same point. Obviously, the largest context length is running on a different data set, so it's not something we can compare with as such. And obviously, it's running a larger sequence length as well. So, but as you can see, that's starting to come further down. In terms of performance, you can see we're essentially running a model with double the size, and so the performance has dropped a bit as well to account for that. As we come towards the last 50 steps, any other questions about using these things, or applications that are interesting to you where these features such as this would be helpful? There's a question on, can the CS2 be used for training RL agents, or is it primarily for supervised and unsupervised learning tasks? A lot of our focus so far has been in the supervised and unsupervised learning space. It depends on which aspects of the RL agents itself. So the model training aspect of it, the CS2 can do, but if you're interested in, can I speed up running, let's say, an Atari game or such, while yes, you can in theory program the system to do those things, it hasn't been an area we've focused a lot of our time on yet so far. I don't know, Richard, if you want to add anything to it.
No, I think, again, with all these questions, these are all valid. I think we've just been in a game of prioritizing what we get the most requests for and where we see kind of both academia and industry moving to. So that's not to say we can't support these things on our CS2, but I think the more we can get these data points, especially from our teammates over at ANL, I think that can help drive, your use cases, because we want to support all of these things and just account for the limited resourcing that we have.
As you can see, again, we've completed this run. successfully. And with this, we've now trained a model with 4096 context length than the traditional 2048. Obviously, if you have a larger data set, a large sequence length, that's very much possible as well. But obviously, to save time, we didn't pursue anything larger than this here.